I have a QSLs, but let me finish this. So, good morning. I hope that everybody slept well. So, let me start the first part of our lectures today morning. In the plan, we have three presentations. Láďa, OK1Dix, John, and Dave? Brian, G4DML, G4SWX, and Max, X-ray Echo 1, X-ray Alpha. So the first part of the conference will be moderated by Dan, HB9 Charlie Radio Q from HB9 Q Club, and the second part will be moderated by Láďa OK1Dix. So Dan, it's yours.
Good morning, everybody. Obviously, the night show was heavy. We have heavy losses, but welcome, and nevertheless, we get started immediately. Lada, please, the stage is yours.
Thank you. So, the audience is coming slowly, it's a good news. And okay, let's start something different than you've heard yesterday. There was a kind of very fine stuff. We saw even some mathematics and things like this. This is a little bit more a real thing and heavier thing, I'd say. So contesting, it's one of, excuse me, good. Why 2-meter contesting? What do we have? Although a lot of people here are more interested in microwaves, and it's a really fine stuff, as I said, there is still maximum activity on 2-meter. Yeah, it is so. And taking part in a contest is a good opportunity to make new initials, DXCC, US states, and so on. So even the expedition take part at the contest. So you may have even microwaves at home, but you might have even a 2-meter antenna with the normal tropo setup, and you can simply try it. Yeah. So. And also, it's a good opportunity to tell friends, hey, you got a tropo setup, so try EME, and the contest is the best opportunity to start. So, after that, some people may be interested. Oh yeah, contesting is good. I made a couple of contacts with my normal tropo setup, and I need to improve my station to be more serious in the contest. So what do we need is about this setup. And with setup like this, like four dual polarized long Yagis, full eagle power. Here in Czech Republic, we are lucky. We have a 3 kilowatts legal power for EME. Yeah. Wow. And yeah, usually it's like 1,500 watts in US and maybe in other countries. And we need for serious work in the contest definitely the dual polarized Yagis. I'd say, if, for instance, if I have a one Yagi, and then I consider how to improve my station, say putting up another Yagi, I'd say, okay, it's not much more work to put there cross Yagis, and the improvement is dramatical, really, because Faraday rotation and polarization change it makes a big difference. So dual, and also dual SDR for adaptive polarization. Let's think that there are a couple of such SDRs like IQ Plus and others, and which enables us to receive like horizontal and vertical polarizations at the same time, and the software then shows you even in what angle the signal is coming, how it is rotated. And for this SDR, the best way, we will see further then, because that's the software which deals with this SDR for adaptive polarization. There are MAP65 and Linrad. So, but by my experience is that sometimes this software doesn't allow you see the traces and everything. It doesn't detect, doesn't decode. So it's always good to have also XWSJT with another sound card, and to do the decoding simultaneously in both, with the MAP65, for instance, using the dual SDR, and at the same time over the normal sound card with XWSJT. And then optionally the Linrad, especially in the high noise area. Here, just a second, here this is. How it looks and how I use it for the contest, which is because we have to realize the time is money in the contest. Losing time in the no decodes periods, it's a lost time. So, and like I said, it's always good to have a dual SDR, like here, with the USB 4-channel sound card, and the software. The software, there is a little problem now, because how I use it is a Linrad as a front end, and the MAP6530 over the network. That's how it works. You may ask, why is here MAP6527, here's 30? The answer is very simple. Unfortunately, MAP6530 doesn't support some sound interfaces anymore. ACO interface is among them, and unfortunately, my sound cards, which I have, don't have any other option how to connect the full 4-channel composite signal. So the only solution is a Linrad and MAP6530 over the network. And MAP6530 is necessary due to new modes, like Q65A and 60 and so on. So someone else may be lucky with another 4-channel sound card, but they are not very common on the market nowadays. The card I use, I bought on eBay, because there was nothing good on the market. So, and so that's the Linrad and MAP6530. That's one option. It has also the advantage that if you work with Linrad, there are great options how to fight noise. The noise is especially on 2 meter, is our biggest enemy, in the city areas especially. So at least partly, we can work with Linaret to fight noise. So this combination I'm currently using. But it's still good to have also the WSJTX program connected to the transceiver. Because like I said, sometimes, although signal is here, decodes doesn't happen for any reason. So here are the splitters. Quite usual splitters like this. They are used in the satellite, in the satellite techniques. Yeah. And to splitter signal after the LNA and the relay, which can switch the horizontal vertical polarization to the TRX. Then audio, the normal, another sound card. That was the reason why I said before that we need 2 sound cards. And then here in a TRX, you can hear the signal. Here, and detect also here with the WSJTX. The transmission, it's because this is another 2 PCs, yeah, and audio out from this. There's a modulation to the TRX for the transmitting. That's quite simple, but this is how we can simultaneously detect in both programs. So now I show how my current station looks like. Its antenna is 8 times 28 expol m square design. This one, like I said, 3,000 watts, full giga power in Czech Republic for EME. Dual SDR and 3 sound cards, as you've seen here, yeah. Because one is this one is this one, and another one for the modulation is internal sound card in the another PC. And yeah, software as I mentioned. So this is how the reception works and how to fight the noise using Linaret and incorporate it into the whole configuration. Here is how the station looks like. Here you can see these 8 antennas on the mast. Here, a little cabin. It was originally it comes from the military, so it's very inconspicuous here, and it's very small, which I mentioned it later has some consequences. Yeah, but this. Please forget this one. That was as I took the picture. We ran there 160-meter contest, so this is a vertical antenna, still was here, but it's not there now. Here is another view of the antennas. And the antennas in the parked position, because now we're coming to some problems with such stations when you, if you want to make a good result in a contest. So the problem is that with such a station, the torque is enormous. It's a huge, yeah. Not the torque when rotating, but the wind load. Yeah. It's well, at the beginning, I wouldn't believe that, how big the torque is. So normally, when I'm not using it, it's the antennas are put a little bit down, and here, I don't know if it's, see, but here are there are 2 actuators, which, when extended, they fix the antenna against the mast, yeah? Because otherwise the normal rotator at the wind like 90 kilometers per hour, it would simply crash. So, another view is here. And here you can also see that maybe it's better on the, yeah, here. This is the rotator, and here is the box on which can be lifted up and put down. And the rotator is also a very important thing with regard to that torque, because the original rotator I used before was really not bad. It was a heavy one, but still, after a couple of years, it's worn in the gear was worn out. The backlash was at the wind. The backlash was like 10 degrees. Antenna was moving like 10 degrees here and there. So, and I was really afraid that it would crash. So, now I'm using SE5 worm gearbox. Yeah, that's a very fine stuff. Originally used for solar panels, solar electricity systems, and it has an enclosed slewing, so the warm contact with the wheel is on, like say, 5, 6 teeth of the wheel, not just one. So if you think about such a big antennas, use something like this. And I must say, you can order it for a really good money from China. Here, this is a motor and this is an encoder. So it comes together. If you order it, you can even configure it. You can say from which side you want to have a motor. You can say which kind of encoder and so on. Now let's take a look at the power. This 3,000 watts. This is my original PA. And this was, it looked like this inside. So there are three GS35 inside of the resonator. And this is a cathode part. And but it's not used anymore because we are in the contest. So in the contest, it's something else than working a new initial or a new DXCC or whatever. So if you start calling CQ, say for 1 hour, 2 hours, which can happen, if you can even invoke and pile up, you will see that the normal PAs mostly get overheated, especially SSPA. So, and the same actually happened here too. There were some other particular problems, like you had to somehow select the tubes which have a similar characteristics. So they are driven about this same power, and other problems. So then there was an opportunity, quite accidentally. I have a friend who offered me a discarded transmitter from the which was used for the OERT, which was a FM standard in the so-called socialist countries before 1989, and with my very good friend, OK1 Bravo Alpha Foxtrot, actually I forgot to mention that the antennas and all this equipment is on his property, yeah, because it's not in Prague, of course. It's out of Prague, and he was so kind, and he's also very good technician, and so he said, okay, we put it there and work together. So we adapted this PA. The resonator looks like this. You can see here the original part of the PA, and this is the new cavity exhaust and so on. The exhaust is necessary, like I said, because the cabin is small, and the heat produced by that, once I remember I had 45 degrees in the cabin. So here is how the resonator looks like. It's a normal design, just bigger, and here you can see the tube which is used there. So here is the power supply. Here I can, it's not quite good to see, but this is an interesting thing. Yeah, it is better, yeah. And this one is a fast high voltage breaker by OK1 Bravo Alpha Foxtrot. It works in the negative lead of the high voltage, and it prevents when arc occurs in a tube. It prevents the destruction of a G2 or other G1, the grids. Yeah? If you're interested, unfortunately this has been published only in Czech until now, but if anybody is interested, I can arrange for the translation and give other information, because it's a very useful thing which saved me, especially with the previous PA, with the GS35, it saved me at least 2 or 3 tubes when the arc occurred, because it's connected with the problem of overheating, because the higher temperature, the higher probability of the arc. So here is like the station looks like. Yeah, the rotating system, it's a homemade. I did it with Arduino, but it's nothing special. It's using that encoder which comes with the router. So no, and the elevation is simply the super jack with normal potentiometer, because in the vertical the diagram is about 6-7 degrees, so it's not critical. Yeah. And now something about the tactics and strategy in the contest. Read the rules carefully before the contest, because especially the scoring. What happened to me in 2017 in an Italian contest, they, which was of course okay, but in order to support CW, they put like 20 points for one CW QSO and only 3 points for a Digi QSO. And simple calculation showed that actually staying in CW is much better, and about 26 CW QSOs brought me like more points than over 100 digital QSOs. So if you want to make a result, read the rules and rethink. Finally, another thing is multipliers. It's important thing in every contest. There is a sum multiplier, and check the development during the contest, degradation, the condition development. So using chats, you use it probably all. Interesting thing, if you decide to call CQ, even with your smaller equipment, please stay there at least 10 minutes, because one QSO takes 4 minutes by standard. So these stations may be busy with other QSOs, so give them chance to show you, like keep you, to give you chance to find you. Yeah, which is here. And don't fall asleep. It might cost you many points, and you may burn your SSPA. Yeah. Here, just about the saving CWs, we can see here, oh, excuse me. Oops. Yeah, the development of the CW QSO is just for illustration. Unfortunately, CW is dropping. I think the good rules in the contests may support CW. So, because me as a CW and contest man, it's to me really sad that CW is not. So, yeah. There are some contest rules and consideration. We have 3 major contests: ARA, DUBUS, and ARR EME contest. This is just a thinking of the scoring and what to improve on the conditions, like I said, to support CW and to make the contest more attractive. For instance, in DUBUS, CW contest, the multipliers, WPX style multipliers, don't make much sense if you make like a 20 QSOs. What is that? And in my opinion, the best rules, they are EME trophy. So that's a really good balance with some improvement. Someone read my consideration, my thoughts. Someone may have a better idea. I don't know. So, yeah. Then, in my opinion, the rules for using the chats, that's the last thing I mentioned, should be unified for all contests, because it's actually a big mess. On one hand, there is a CW DUBUS contest where is a chatting not permitted at all, which is, in my opinion, is wrong, because at least CQ frequencies should be allowed. But on the other hand, in ARR contests, there is no regulation. And again, in my opinion, the best rules are in ARA contest when I5 BWE put them directly in the contest rules. So examples of allowed messages and not the message which shouldn't be used, at least in the contest, to make the contest fair. Okay, thanks for your attention. Any questions? That's it. Thank you.
Thank you very much, Lada. Well, just one comment. If you like CW in contest, go to 23 centimeters and up. So, well, but it's unfair, I know. Okay, so now it's getting interesting. Now our English friends are coming and mixing up everything, I guess. Okay, John, it's yours.
Hi, good morning, everybody. What we're going to talk about today is, we put it down as 144, but actually rethinking Yagi arrays. Both of us are very lucky to be retired. We've done just a little bit of 144 EME, DXCC, WAS, all fairly easy these days on 144. And we've had quite a lot of antenna arrays, nearly all 4 Yagi arrays, many of which come down in the storms. But almost every array that we've had today for working 2-meter EME has failures. And those failures come down to noise, really. What we want out of an EME array is to receive weak signals for most of the month. We are not, on 2 meter EME, it is active almost 24/7 and about 26 days out of 28. So it's not like it used to be 30 or 40 years ago when everybody comes on for the best weekend. It is active every single day from moonrise to moonset. And even when the sky temperature is very high, you will still find people on to have QSOs if you can hear them. So we want to receive weak EME signals most of the month, including at low elevations. And that is a very important thing. To be able to be big, because we're in Great Britain, to be usable in the rain, because rain really adversely affects Yagi arrays. Reasonable wind survivability. We have very high winds. I live on the coast, Graham lives inland. And affordable, because we're both poor pensioners, honestly. And we both have amazing noise from terrestrial sources. LED and house and road lighting systems now. As you say, you can hear road lights many kilometers away. Noisy solar panel systems from the regulators and the equalizers. CCTV systems tend to be electrically very noisy and radiate a long way. Because we both have rural QTHs, we suffer from noise from farm workshops because all sorts of things use switch mode power supplies these days. And although it might seem strange for people living in the countryside, noisy villages and towns. Okay. Low elevation at 144 is an issue, right? Low elevations require high antennas to bring the ground reflection of the first lobe low down. But that has a problem. Let's come up in one. Let me use the pointer. This is just a modification from ON4KHG's slide at EME 2012, where he talks about ground gain. Ground gain has its opposite as well. So to work right down to say 1 degree or less, I have an 18-meter high tower. That makes the first Fresnel zone for my ground reflection start at about 110 meters, but go out to 3.6 kilometers away. Now, the scale isn't quite the same. That's my QTH in the countryside. That is a major highway, or a small highway. And that is a town, and that is a village. And you say, hey, that's not bad, because that starts about 95 degrees, and up at 52 degrees north, the moon will quite often rise 45, 50 degrees. When the moon rises much over 80 degrees, I have noise from there that is 5 or 10,000 Kelvin on the horizon. So, and the answer is possibly lower the tower down, lower your noise. In other words, you decrease the Fresnel zone, you decrease the amount of pickup from the town. But hey, I want to work moonrise because my window to ZL perhaps is only up to about 4 degrees above the horizon. And if I don't go down to 1 degree, I do not work other Pacific stations. It's just not possible from the UK. So, what do we think about doing about that? Tradition, and a paper by V7BQH recommends G over T stacking We'll do more of that in a minute. And it's very clear. In a classical sense, G over T is the signal-to-noise ratio derived by the division of the antenna gain and the receiving system noise temperature. That is well defined by DG7YBN. And in fact, DJ9BV, the derived measure of G over T ratio is very suitable. It's a quality factor to compare different Yagi constructions and different stacking schemes. So that's been known for a very long time. There is a problem with it, though. We're English, so it has to be the gin over the tonic, right? And that has to be a must. Okay, so if we build, for instance, a 4 Yagi 2-meter array, can we derive G over T for it? Do we have a picture of the received antenna temperature noise in all directions at all elevations over 28 days? Well, probably not. We can produce a calculation of the celestial noise on 144. In fact, WSJT has got it done in 15-degree segments on the sky, and it's not bad. We can get a measurement of noise for terrestrial sources over 300 degrees is the way the moon goes, but say 360. We could possibly write some software bringing in all these factors in a major program to calculate the received noise at the antenna, full pattern, for all lunar headings in any particular month. But actually, what would that tell us, and how do we improve things? It gives us a real problem. Now, Del 6WU, in his formula, defined the maximum gain that you could get before the power started going off into the side lobes for an array. And it's true from the work of EV7BQH and many others that gives you the best noise temperature of the G over T when you're beaming up in the air and there is nothing else except the celestial noise in the side lobes. There is a real problem that this is no good when you have the real world and 144 megahertz. We've done the work on 144, but I believe it's equally true on 50 megahertz and 432 megahertz EME. We would say that because the assumptions made in the V7BQH calculations, which have been copied by many and become a religion in antenna manufacturers, they're wrong. It takes a beam heading at, say, 30 degrees elevation and a ground temperature. You can vary both, but hey, my side lobes aren't at 30 degrees, and they vary depending on the length of the Yagi and the rest of it, so that the answers you get are not necessarily what you do. If you take either DL6WU recommended stacking, or some antenna manufacturers are getting into a game now. They call it recommended G over T. And what they've done is they've taken the V7BQH criteria and then optimized their stacking for the best of that criteria. The problem is that often results in 11 dB first order side lobes. And it's really easy. If one of those happens, where you have a noise source, either on the ground or even during the month where you see the center of the galaxy, you have more than 5,000 K noise source, and that will enhance your noise temperature of your antenna by 400 Kelvin. Now, it's 400 Kelvin is atypical average noise temperature on 144 meg EME if you operate for most of the month, you have suffered a 3 dB signal-to-noise degradation for that optimized stacking. So we did a lot of modeling. We would recommend reduced stacking distance. We would recommend minus 14 dB for the first order side lobes. That changes everything in terms of commercial aerials and what you can do. At minus 14 dB, that reduces a 5,000 Kelvin to only noise source to only 200 Kelvin to your antenna noise temperature, so that you haven't got 3 dB increase anymore for some of the time, not all of the time. But it also results in smaller array stacking distances, perhaps better survivability. But the design must be really carefully optimized. We have done a lot of work in modeling for Yagis in 4 Yagi arrays. And it's essential to do modeling to understand Yagi stacking compromises, because not all designs work well outside the DL6WU criteria, because that is where the commercial antenna manufacturers have designed antennas for the beauty contest. And as I said, we've already decided we don't like the beauty contest. It's essential if you want to change anything with the published Yagi design or evaluate what commercial Yagis will do if you change things. Our preference is 4NEC2. Lots of people like other programs, but I don't understand why. It's free, or you can use an NEC4 engine if somebody else has paid, right? It allows, and what we have done is made every parameter an algebraic variable. So nothing is fixed as a Yagi design, everything is in algebra in the precursor program. This means we can change anything and optimize anything. It also means that we can re-optimize the Yagis in a 4 Yagi stack, so we can change the Yagi dimensions, element length, spacings, everything, once we've built a stack, and we could see the variations in the side lobes and the rest of it. After a lot of modeling and testing a lot of designs, we chose a modified OWL, which was from G0KSC, which is a modified DK7ZB design. And we chose it because the gain stands up best for a given boom length as you close in the stacking. It's not ideal. I would have liked minus 17 dB first side lobes. That would have been a lot better. So the results of the modeling is quite easy. We've designed and built XPOL aerials for obvious reasons on 144 EME that we want to receive both polarizations. As I've said, optimized DL6WU stacking generally results in minus 11 dB first order side lobes, but it's not quite the same if you use symmetrical stacking. And so what we did is we optimized it for minus 14 dB first order vertical side lobes, because the real problem is you start elevating, you see noise sources that are at ground level. And so we went through a massive process of, if you go for minus 14 dB first side lobes, how much gain do you lose? Well, Graham lost about 0.35 dB in a much bigger antenna, which is 5.3 lambda. I lost about 0.3 dB. But the answer at the end of the day is that we now have Yagi arrays that are more usable at low elevations and we don't suddenly get death when you see a high noise source. And all we've traded off is about 0.3 of a dB. The other thing we got out of modeling is the design of XPOL antennas. With an XPOL antenna, you have two Yagis on the same boom. Most manufacturers make it easy, and they make the two Yagis a quarter wave apart. So it makes generating circular polarization very easy, put the same length feeders in. What we did is, because we have models that are totally flexible, we looked at changing the spacing between the two Yagis to get the minimum interaction. And this is my 5.4 lambda Yagis. That's the vertical and that's the horizontal plane for the horizontal Yagi. And the vertical Yagi has a small difference in front to back, but that's minus 25 dB or so. So the single Yagis for the XPOL are within a fraction of a dB.
It's my turn. Okay, right. Well, thanks, John. So after all this work, I got the job of building it. Yeah, thanks, John. You know. Hang on, I've just got to figure out how to use this thing, I guess. Right. So first thing is I've built many antennas. Usually they don't work. So this time I thought we'd give it a go and really do it properly. So I quickly built a waist-high, 7-meter long bench. And we were determined that if this was going to be a workable solution, it would be easy to build, cheap. I'm a cheapskate, I'm a pensioner. You know what the UK pensions are like, useless. It had to be not expensive, reliable, and in my point of view, I have a lot more noise sources than John, so it had to be as per the design, which meant a bit more accurate than I normally do things. So we came up with a set of sort of, I suppose, imaginary guidelines. So it had to be very safe to use in wet weather. We do tend to get a little bit of rain in the UK, so the elements tended to we thought would have to be larger diameter. My current antennas are JXX XPOL, and that's completely unusable in wet weather due to the high Q and thin elements. So 8mm tubular elements, 38mm round pole as the boom joined together several times, obviously, because that's very cheap. Elements through boom, as you can see there. Just using a nylon top hat and what's called a star washer, a push nut, in fact. We had to select that. That took a lot of time because when you push those on, it's really designed for steel. If you push it on aluminium, it does a lot of damage. So we found some that would hold it firm enough, but wouldn't damage the aluminium too much. The only tools that we used were normal workshop things. I bought a simple jig that took an angle grinder to cut all the elements and all the aluminium, and I also had a stand drill where the drill moved and the bed stays still, so that when you're drilling things with a different length drills, you don't have to keep repositioning. And I also built a couple of wooden jigs to hold the round tube so that you got a very accurate vertical drill every time. So that was basically how we started. We also had the idea of a 12mm aluminium folded dipole, and 12mm with 1mm walls fits exactly 9/16 US measurement, 9/16 for the ends, the loop ends of the dipole. So very simple, easy to make. You can build one in a day, really. Right, is next that one? No, next is that one. The feed, I'm not sure this is what we will end up with, but this is what we have at the moment. It's looking for a feed block, and antennas amplifiers just happen to have one in stock. It fits a round boom. It comes complete with everything you need, except it is a little bit expensive, but it solved the problem, as you can see, of how we would mount the dipoles. 12, as we said, this is 12 mil, 9/16 ends, stainless steel clips to hold that in place. The feed is RG142, which is rated certainly at what we're allowed to use in the UK. Yeah, 1800 watts actually, but that's of course more than we're allowed to use in the UK, John. Yeah. Anyway, with 5 ferrite beads giving a really good high impedance at 2 meters as a choke balun. Basically, that then fed back to a block at the end with 2 inline N-types, and John decided that he would make these different lengths so that these are actually in phase at the antenna. I haven't decided whether I'm going to do that yet, but that's that. So John will be has put his phasing off the antenna, so that's actually in phase there. So prototypes, this is my back garden effectively, and on a little trailer, that's my prototype antenna, and that's John's prototype antenna. Basically, we had that up at about 5 meters, and about 50 meters away, we had another 5-meter pole with one of the, I'm sure you've seen them, these little seed RF generators. You can get them from the Far East. They're about, I think about 100 quid or something like that as a signal source. And on a test rotator, after doing the initial measurements at the antenna, this was all fed back into the shack where I've got some servers in there and various other bits of test equipment. So thanks to Richard for CDN down there, wave Richard, who gave us some necessary muscle. And this is us adjusting the length of the trombone to get exactly what we wanted. For example, this was the plan. This is from the design. And as you can see, this is my antenna getting about, typically we should be planning to get about neg 28 return loss on 144.1, and we're actually getting neg 28 return loss on 144.2. My suspicion is that we've just got the through boom correction slightly wrong, probably 0.5 millimeter, but I use the SM5 BSZ. He did a very good synopsis of, there's about 20 different methods of measuring the through boom correction. When you put an element through the boom, you have to make it slightly longer. And in this design, it calculates out to be somewhere between 5 and 7 millimeters. I chose 6. I suspect that isn't quite right, but it's close enough. But as you can see, the design actually comes out incredibly close to what we actually measure. This is measured, by the way, on the mini VNA tool. I think they're about 60 or 70 quid. And that's short for pounds, so about 100 euros. And you can, there's a little bit of software that you can run on a laptop which takes that and displays it nicely on the screen of the laptop, so you can cut and paste as I've done here. So you can see the return loss between 144 and 144.5 is really, over 23 dB, which is very good. And in fact, it is over 20 dB, pretty much all the way up to 146. So it's a really wide band. I did, during this phase of the tests, soak the antenna for about 3 or 4 hours with a hose pipe, so water was absolutely running off, and it really didn't change it very much at all. So really happy that's come like that. So this is the measurements. So really, really impressed with, I don't know if you've seen this program, but it's a little program written in Java by Graham Freeth. I forget his call sign. G4HFQ, really nice guy. I had a bit of a problem getting the audio so the way it works is basically you've got a receiver receiving the signal in from your antenna. You turn the AGC off. You make sure you get an audio tone by using, CW settings on your receiver or whatever, and then you just it automatically calibrates. So you just turn it round 360 degrees, and as the audio changes in level, it records that, and at the end of it, draws you a polar diagram. And that's the design, what the design should look like, and that's what I actually did on the first plot. It's slightly wobbly. It was a windy day, and the antenna was wobbling around a bit, and there's a couple of little things. The front to back is different because we didn't realize that it would see the dish, my 4 meter 23 cm dish was about 10 meters behind the antenna. So as it was turning round, it was actually getting some artifacts from the reflections off the dish. And secondly, this little funny lobe here, that is my next door neighbor's CCTV system, which was on, and I'd forgotten to ask him to turn it off. So as the antenna went round, it picked up the noise from one of his cameras. But you can see, if you ignore those two, the design, this is my antenna, should be coming in. The scale is slightly different, but at about neg 17, neg 18, and sure enough, that's exactly what we received on that plot. So it's really very, very accurate. It even calculates the gain, and the gain just purely by the beam width, and that was coming out very accurate as well. So it's well worth having a bit of a play with that. It's freely downloadable, and it's just good fun if you want to plot the polar diagram of your antennas. Am I doing for time? Okay. Right, so, and there's John's antenna. Again, artifacts at the rear purely because my dish was in the way. But as you can see, all the side lobes look pretty much similar. So really, really excellent tool. It helped us out a lot. Graham helped us out because I had used virtual audio cables between my servers, and the software wasn't handling that very well, so he gave us a little update, which was good. Oh, right. I decided I was just going to mount my antennas in the normal H pattern. John, of course, being different, and his antennas being a lot longer than mine, decided he was going to mount his antennas in an X frame. So if you can imagine, this is the center boom of the X. So the X center is the thing you're going to rotate up and down to get the elevation. So that's the elevation mechanism as built by us, well, designed by John, built by me. And that's a 10 mil aluminium plate with a standard HARL or QARL jack, which is incredibly powerful jack. Using another superb elevation measuring device is the Level Developments level sensor, made very close to us actually, about 50 kilometers from where we live. And it's a superb device, outputs an analog output between 0 and 5 volts or thereabouts, over 90 degrees in 1,024 steps. And that's what it looks like. So there's the boom down the middle, there's the jack, and there's that plate, as you see, and these are the X's that support the 4 antennas on the corners. A big brute, I have to say. And that's on a heavy-duty 80-foot. Yeah, 12-meter boom, steel, partly steel, partly aluminium, just to get the moment right. And yeah, and there it is, elevating. So, results. This is what we get. As John, I think, has already said, we were aiming for 14 dB down side lobes, and we ticked the box on that one. I wanted around about a 19 dB gain with closer stacking than the recommended figures. That's both the mechanical point, and secondly, I really did need to keep those side lobes under control. I have many more noise sources than John, and it's imperative. I get 10, I've got probably 4 or 5 10,000 Kelvin noise sources within the rear of my antenna and on side lobes. All working as per design. So, summing up. There is nothing wrong with G over T. There is G over T. There's certainly nothing wrong with that, except it's the wrong way round. But G over T is a great way of just assessing a single antenna in an ideal situation. And there's nothing wrong with that. It's how I'm sure when you buy a car, you buy it, and it says it does so many kilometres to the litre. You don't believe it, but it's a good metric between vehicles. So there's nothing wrong with G over T as a measurement. But when you stack antennas that have been designed as single antennas and you don't design them as a set of 4, really, and I can vouch for this, for example, the I0 JXX antennas, the side lobes are really out of control if you stack it too close. So when you want to shorten the stacking distance to get the better side lobes, sometimes it doesn't happen because the antenna wasn't designed to do that. So that's why we decided to design it as a block of 4. Modelling essential, we use the NEC 4 engine. There are others. We believe that the antennas have cost something like, I think mine cost about 60 euros, yours probably cost about 100 euros to build one antenna. And we had great fun. A lot of gin and tonic was drunk, and some arguments, but it was good fun. So we have 8 antennas. I haven't put mine up yet. I've still got to put I've tested them, but I've got to build a new elevation mechanism. But we've had fun, so thank you. Oh, I've got one more slide. Oh. Question. Is that for John or for me?
Have you considered introducing a phase difference between the upper pair and the lower pair?
Yes, you have.
To reduce the lower side lobe. And it costs slightly of the gain, but not more than you would have for stacking.
Yes, but what you do is if you change that, you change the skew of the side lobes. In other words, if you do it in the vertical plane, your upper side lobe goes up as the lower side lobe goes down. And if you want to use this throughout the month for 26 out of 28 days, there will be times when your upper side lobe is pointing closer to the center of the galaxy. And that is really not very good. And also, not to mention the sun. If you raise that upper side lobe to say, I don't know, -9 or -10 dB by suppressing the lower one, and you put the sun in the first side lobe, you will see it. So we understand that. I've looked at it, but we decided to close the stacking down.
Maybe you could find a scheme to switch
Anything's possible.
Yeah.
Anything's possible.
Oh, Paul.
You show nice EMH plane plots. Have you ever looked at 45 degrees?
No. What I have done with mine is I've done plots of the near field, because in the UK with a high power permit, you have to have a near field calculation. So I have a near field calculation for my array. Yeah, so it's great.
Yeah, but yes, thought about it.
What is the influence of the H-frame and the coax cables?
Well, I don't have that problem because I use an X frame. The X's are made of glass fiber, and we feed the antennas, both of us feed the antennas from behind the reflector. That means that we don't have coax in the plane of direct to one, which is the greatest field and the greatest current.
And your tower?
Heavy duty Versatile.
Yes, but is the lowest antenna above the top of the tower?
No,
Tower in between?
it sinks down below the top of the tower. So,
Do you know any influence, any figures?
I only from actually testing it. It's the lower antennas are the problem. You've said, we all know that. The bottom one's on the H frame or John's on the X. I have tested that, and actually even with the closer distance, I can't detect anything on the plots that I'm doing. But everything else is fiberglass. So the cables are behind. They drop down and then are taken down a central peak to the mast, and I can't see anything. I've done it. I even tried it on a fiberglass pole, but you've still got the cable. So yes, it's who can say. Anyway, I think time's up. So thank you.
Thank you, guys.
Oh, I can drink.
There's only gin left. Hello, Max, welcome. And we go back to a little higher frequencies now. Yes. And optimizing also here. Yes. Okay, please, it's your stage.
Greetings to all of you. Thank you for coming here today. Well, this is a project that I have made about 2 years ago. And the purpose is to do a comparison between the measured performance of a septum feed, like the OK1 DFC unit, with a properly designed horn flare adapter against the same feed alone and with a choke ring. So the control is here. Okay. For lack of time, I'm going to skip the first part of the lecture regarding the flare calculation. You could find it in the proceedings. No. Okay. So well, I'm going directly to measurements and results. So we have here a 4-neck-2 simulated polar pattern of the OK1 DFC bare septum feed polarizer located at the focal point of my dish. That is a dish with an FD of 0.4. So what we see here is that the half beamwidth at minus 10 dBs is well out of the subtended arc of the dish. So all the energy outside is spillover. And this is a simulated polar plot of the septum polarizer with a flare horn adapter. You will see that the results are pretty close to the calculated values. Why the calculated values? Because we are now shaping the radiation patterns to have a half beamwidth at minus 10 dBs at 53 degrees, and the half beamwidth at 65 degrees at minus 12 dBs. Why minus 12 dBs? That is very well explained in the first part of the lecture, but I'm going back And you will see that final calculation for me was minus 11.73 dBs. So if you are doing the comparison between the OK1 DFC Berset tune feed and the one with the flare, you will see a big difference in the rear and back lobes. And the shape of the patterns is different. So at this point, what I've been doing is to do a somewhat manual linear plot of my 5 meters dish equipped with the flare septum polarizer. You will see a clean main beam pattern with 2 shoulders that are representing the first side lobes. I would like to make clear that those 2 side lobes are exactly equal. Yes. Okay, okay. On the top, okay, perfect. And the problem is when you are doing a manual plot, you have to take note of the sun elevation angle and then write on a piece of paper the value you are reading, so you are losing time because sun is moving very fast. I have been calculating the normalized relative level of the side lobes, and the value is minus 18.87. And I think that that is the right value to get the best GT ratio. Well, now the next step is to find the best relationship between the GT ratio and the system temperature. When the beam width of the feed is adjusted to properly illuminate the dish, what we are doing is to optimize our system GT ratio, or figure of merit. When the beam width is further reduced, the GT ratio will drop below its maximum value. So we have here the formula. GT, you will see 8 pk Kelvin constant, some y minus 1, divided by the solar flux multiplied by lambda square. It will be easier to visualize the weight of the involved parameters if for a set value of solar flux we call the red numbers 8 pk divided by flux multiplied by lambda square as a constant factor. Then we have that the figure of merit is equal to the constant factor multiplied by some y minus 1, where G is the real gain of the antenna multiplied by its efficiency, and T the system equivalent noise temperature. So that obviously some y is directly proportional to the dish effective gain, and the T system is inversely proportional. Then we have another y factor that is derived from the measured ground to cold sky ratio. That is the formula. By under-illuminating the dish, the Y factor will increase, but the dish efficiency will decrease. There are, in my opinion, two indicators telling you when you will reach the maximum GT that I'm calling the break-even point. When the first side lobes are down at minus 18 dBs, you will lose just about 1 dB of gain, taking into account the edge illumination taper. When you reach a measured Y value with no further increase in some Y. Maximum sum Y means maximum GT ratio and maximum own echo signal strength. Optimizing the beam width for a feed designed like the OK1 DFC for an FD of 0.3 up to 0.35 to fit a dish with an FD of 0.4 with the proposed flared horn adapter makes a difference. By testing an experimental feed that is not listed in the VK3UM calculator, you could now be able to calculate the involved parameters and compare results. For example, with the listed set values. Those values are those that I'm measuring with my own dish. Measurement having been made more than 2 years ago on quiet sun, so you will some value different for actual values. So I've been measuring 15 dBs of some Y, my receiver equivalent noise temperature, 18 degrees Kelvin. The LNA has a noise figure of 0.26 and 36 dB gain. So there is enough gain to consider that the noise temperature is 18 degrees. The constant factor has been calculated is 1.444 for a set solar flux of 45. And what I'm doing now is solving the former equation, this one, the Y, for the antenna temperature. So that is the formula, and it is quite interesting because you have the Y factor both at the numerator and at the denominator. A small variation in Y will produce a larger variation in the antenna temperature. The result for me is 59 degrees Kelvin. It could seems too high, but this is the temperature from the LNA input, considering all the losses to the antenna. So I don't know if you have been measuring the sound Y you are getting with and without the protection relay. I'm doing that, and the difference is quite large. So we have now a T system that is the sum of the T-ant, but TRX of 59 plus 18, 77 degrees Kelvin. So, as we have seen before, G divided by T system is equal to the constant factor multiplied by some y minus 1. So we could calculate the real gain of your dish. That is, in this case, 3,405. But the theoretical formula to calculate the gain for a dish is that 1. So we could now be able to calculate the efficiency. The real gain is that 1. And the theoretical gain is this 1. So the efficiency of this system is 73.6%. Different methods of calculation make a difference in the resulting T-system value and dish feed efficiency. The VK3 calculator is considering T-system equal to T-spill, spillover, TRX, T-feed-through, and T-sky. But into the antenna temperature, there are other factors like scattering and reflections from feed supports, edge diffraction from the dish rim, aperture blockage, and dish surface losses that should not be underestimated. Well, this is a choke ring feed design courtesy of W1GHZ. You will see that in the real world, the dish efficiency is reaching a value of about 75%. Sorry. This value. That probably looks more realistic than the calculated value of 80.4% derived from the VK3 calculator, because the VK3 calculator is taking in account only mesh, feed-through, and spillover. According to Henry Jasic of the Antenna Engineering Handbook, the best mathematical work predicts a maximum dish feed efficiency of 74%. Therefore, we must be satisfied to be able to get close to reach such values. And conclusion, when the horns flare is properly designed for a set FD ratio by putting the first side lobes down between minus 18 and minus 19 dBs, you will reach the maximum GT system ratio. That means the maximum signal strength of your own echo and the best receiving performance for your system with a minimum feed blockage. I'm going back to the beginning. Well, this is well explained, all the method of calculation that they've been following. And I think that I'm not the only station using actually a flare. The flare is working very efficiently if well calculated. I think that my results have been that with the septum with an added flare. Some Y value has been a little better than the value I've been getting with the same illuminator and the choke ring. That's all, basically. Thank you for your kind attention. If you have any question, please raise your hand.
No, it's good, good. Any questions? Oops. Any questions? I take this one. Any questions? Yes, Charlie?
You mentioned with the minus 18 to minus 19 side load level. I think in an earlier slide.
Wait a minute, Charlie.
Yes. I've been following the guidelines of OM6AA. And I think that if I lose maybe 1 dB of gain, I'm gaining with a lower system temperature. And for me, that point is what I'm calling the break-even point, the best point that you have to reach.
Yeah, I understand, and I think you've got a very good working system and you've optimized G over T brilliantly. But the question was, you've compromised on under-illumination to get best G over T, and you stated earlier that that would reduce dish efficiency, but you got 74%, which is nearly the theoretical limit. So I was just wondering how you've managed to get such high efficiency with a little bit lower illumination to get best G over T. That was the question.
Okay. What I've been deciding when calculating the flare is to under-illuminate the last 5 degrees around the rim of my dish to improve the reception with a lower temperature.
Any other question?
Well then, thank you very much, Max, and have a lot of fun with your optimized system. Thank you, gracias, muchas gracias. Okay, now, next step, it's ready, coffee time. Please be back punctually in half an hour.